Network-connected embedded systems will need to have a secure update facility. You'll need to deploy security patches if you're on a network, or your code will become vulnerable to attacks. Even if you think your code is perfect, which it's not, third-party code that you incorporate will have discovered vulnerabilities and will need to be patched, including libraries, the operating system, communication protocol stacks, and so on. So you'll need to do updates, but you'll need to make sure they're secure. In particular, you'll need to make sure that only legitimate updates are added to your system, since an attractive method of attacking your system is to install a bogus update that has malware embedded inside it. To do this, you'll need not only to validate the update, but also to have a secure bootloader. That means you need to make sure any updates installed are okay, but you need to do that not only at the time of the update, but also when you turn on your system. Otherwise, an attacker can compromise the bootloader itself, bypassing all your security checks. To do this, you should use a two-stage bootloader. The first stage is as simple as you can make it, very limited functionality that knows how to run a second-stage bootloader. In particular, it does a cryptographic integrity check on a second-stage bootloader and runs a second-stage bootloader, and that's all it knows how to do. The second stage knows how to update itself, how to load application images, and so on. This makes the second stage much more complicated, but that's okay. The reason you need two stages is that you need some piece of software that cannot be changed without physical access to the computing system. Otherwise, some attacker will find a way to update it remotely and compromise your system. But because that part cannot be changed, it has to be right, or else you need to do a physical recall in the system. So the idea is the first stage is, for all intents and purposes, hardwired into the system, but it's just smart enough to validate that a second bootloader is cryptographically secure and execute it. And that second bootloader does whatever you need to do to run updates, to launch the system, and so on, but it can be updated because you have a resistance to attack in that the first bootloader will only accept validated second bootloaders. Now, what does a bootloader do? Both the first and second bootloader have the same secure boot features. What they do is take a public key that's hard-coded into the bootloader and use that public key to validate a signed second image, the second bootloader or the application. Only properly signed images are attempted to be executed. This ensures that only legitimate, authorized images are executed rather than images created by a malicious attacker. A couple flourishes on top of that are, first, consider limited date ranges for validity of a signature. Many times, internet connectivity is intermittent or difficult to achieve, or there are other constraints that make it infeasible to use a public key infrastructure. So how do you know that an image is legitimate? You do this by hard-coding a public key in to check this digital signature. Well, that's great, but what if over a 10 or 20 or 30-year lifetime of a system, someone compromises the public key and now starts signing fake updates? A potential mitigation is to have signatures only valid for a window of time, 3 months or a year or 1 month, depending on your system. The idea is that generally there's a way for the system to know what the current date is by asking the user if nothing else. And the system will only run updates that have been signed within a window around that date. While this doesn't prevent a key that's gotten loose from causing damage, it does time limit it in that that key can only be used to sign firmware updates for a window of time. After that, the system needs a new update, which should be no problem to sign with a new key for the factory, but will cause the attackers to need to keep capturing digital signature keys. And if they can do that, you have bigger problems. Also, consider hard-coding the repository IP address. Now, this can be an issue if somehow you have to change an IP address for your internet source of updates. But one way to design these systems is that they will only look for updates on a certain server to make it that much harder for a malicious source to advertise that it has updates when in fact it's not the actual system design and maintenance organization.